Hey everyone, welcome back to my channel. In the first part of this project, we uncovered that 20.4% of customers had churned, and more importantly, why it was happening. In this video, we move from understanding the problem to predicting it. So, the second task is about building a machine learning model. We've already laid a solid foundation by exploring and preparing the data. Now, it's time to apply machine learning techniques to build a predictive model for customer churn. A crucial step in enhancing SmartBank's customer retention strategy. Let's get into it. So, in this task, we are going to select the right machine learning algorithm and fine-tune it to accurately predict which customer are at risk of leaving. This model that you're going to build will provide actionable insights, enabling the team to develop targeted intervention to retain available customers. So, as a data analyst and a data scientist, this is what the job is about. We are going to build a model here that not only predicts the churn, but provides clear indicators of why customers are leaving. We would choose an appropriate algorithm, like I said. We would train the model and evaluate its performance. The goal here is to create a model that can be easily understood and acted on by business stakeholders. All right, so let's go. For this project, we are not only going for, say, prediction accuracy. We are also understanding why customers churn. Logistic regression gives us something very important in a business context: interpretability. We can clearly see which features increase churn risk and which ones reduces it. Other models like random forests or support vector machines can capture more complex patterns, yes, but they also make it harder to explain decisions to stakeholders. And in real world projects, a slightly less complex model that people trust is often more valuable than a black box with marginally higher accuracy. So here, logistic regression serves as a strong baseline model that balances performance with transparency. And once we establish that baseline, we can always compare it with much more complex models if need be. In this project, feature selection is driven primarily by exploratory data analysis. The goal here is to retain features that are both predictive and inseparable, rather than aggressively reducing dimensions at the cost of business understanding. In this part of the project, the goal is to move from analysis to prediction. Using the datasets we prepared in task 1, we now need to build a machine learning model that can identify customers who are likely to churn. Customer churn is a binary classification system, and there are several algorithms that could be used here, including decision trees, random forests, or gradient boosting models. However, in this project, I will be starting with logistic regression. The reason for this choice is balance. Logistic regression provides strong baseline performance while remaining highly interpretable. This allows us not only to predict the churn, but to clearly explain which factors are contributing to customer attrition. And once the model is trained, Performance is evaluated using metrics that are appropriate for imbalanced data, such as precision, recall, F1 score, ROC-AUC, and the confusion matrix. All right, so the next thing that we are going to do is build a model. And to do that, we first need our data set. So we navigate right back into it. And so I'm going to rename this customer churn data. Yeah, customer churn data. And then we just export as download as CSV. So now we have it. All right. Now the next thing to do is to go into Visual Studio or any IDE of your choice. I prefer Visual Studio. All right. We create a new file, say churn model.py. All right. Then we create our file, and there we go. Yeah. First of all, we need to import the data set, but before we do that, we will need to import the data set, and to do that, we will need our libraries. You know what? Let's just add numpy in there. As an art. So yeah, pandas will handle the data loading and manipulation, and then NumPy will handle the numerical operations. So yeah, so we just import the data sets. All right, so what I did was go into my folder, into my file explorer, and then moved the data sets into the SmartBank folder with which we are working. This makes it easier to locate the files and copy the relative paths. So just, yeah, there we go. Yeah, so we just, and then we copy the relative path and put it on the booyah. Next, we just load, we just check if it's working. To check if our data set has been properly imported, just run a dot. Yeah, let's see. All right, so as you can see, we have our data sets. Yeah. All right, so let's just move forward. So now what you're going to do is that we are going to separate features and targets. So this what this does is that it avoids target leakage and then it keeps the modeling clean. All right. Let me just what I'm doing next is that so now identify we pull out the categorical and numeric columns so that Python knows how to treat the columns. All right. So next we'll start building the preprocessing steps, and to do that we will need to go back and import some stuff. Now let's set up the actual preprocessing. So what this does is that it we are applying the right transformation to each group. Yeah. For the categorical, we apply the categorical transformer, and then for the numerical categories, we apply the numeric transformer. Now we are next we will split the datasets using the train test. That's the train test that we did earlier. Okay. So what we are doing here is that we are using 80% of the data for training, and then we use the 20% for sensitive testing to preserve the churn ratio. Now we will build the model pipeline, the logistic regression model pipeline. So model pipeline. Okay. To build a model, the logistic regression, we need to go back and once again make some more imports. Okay. Okay. So now we'll build the actual model. We are going to call the model and then put in and handle the chain balance. Yeah. So let's do that. So we'll set up the script that trains the model CLF. So there we have it. This line trains the model, and then we'll go into the prediction. Now here we would write the lines of code that will make the prediction of the chain class, and then we'll add the chain probability in there as well. All right, so now we would evaluate performance to see if what you're doing is actually what we wanted. So we would look out for precision, we look out for recall, and then F1 score. All right, so yeah, but before that, we will need to import some stuff like the classification reports, library, the confusion matrix. So let's just do that quickly. All right, so now we can write the line that will bring out the. All right, so there we have it. We can run the model and see how it goes. If it goes fine, we continue. Otherwise, we go back into the code and then make changes. All right, so okay, so yeah, we forgot about map. Yeah, I should do. Jeez, another comma. Okay. Sure. Okay. First of all, let's comment this out. I don't want to print the head again and then look at what's wrong. Okay, where is it? Line 54. Okay, here. Okay. Okay, so what I'm thinking is that before we even get here, normally we need to call from a list. we need to call from a list, not from a set. And so when we use the CLF to create the pipeline, curly braces in here, Python uses to create a set, not a list. So yeah, we would need to change that quickly. All right. I think they should do it. Let's run it again and see. Okay, another error. Okay, let's just rewrite this pipeline again. Let's rewrite this pipeline again. Okay, so hopefully this fixed it. Let's go again. Okay, so this is what is causing us problems. The marital status. So it seems as the name that I told it to expect is not a name that's there. So it's a column name mismatch kind of thing. And I checked in the data set and it seemed I put a space in here. So yeah, hopefully this fixes it. Let's go again and see. Another error. Okay. Oh hey, yeah, a different error. So yeah, it seemed we handled the marital status issue and now we are having something in line 50, 57. Okay, yeah. All right, so let's see. Okay, so what I'm thinking is that X test is a pandas data frame, and this is a numpy and star index. Yeah, yeah. So it was a mistake that I did. So basically, I was trying to index a data frame like an numpy array, so, and pandas is throwing a an error. So we just fixed that. All right, so let's solve that quickly. We just replace that with yeah. Let's see if this will work. Let's see if this will work. Finally, all right, there we go. We got it. All right, so yeah, let's interpret the results. We have an area under the curve of 0.52. Hmm. This is barely above random guess. It's like a coin flip is 50-50. So technically, the model is learning, but it's not enough to be useful yet. That's fine. That's fine. So class 0 has a precision of class 0 has a class 0 has a precision of 0.79 and 0.79, a recall of 0.56, F1 score of 0.65. So this model it's fairly good, and it's fairly good at identifying retained customers. When it predicts someone will stay, it's usually right. And it also catches a little bit over the over a little over half of the retained customers. So it's fine. Most customers do not churn. Okay, so the chain customers here, this is what you're actually dealing with. A precision of 0.2, precision of 0.2, recall of 0.41, and F1 score of 0.27. So a recall of 0.41 means the model only catches 41% of churners. And the precision of 0.2 also means that 4 out of 5 customers flagged as churners are false alarm. So from a business perspective, too many real churners are missed and too many loyal customers are wrongly flagged. This model is not yet reliable for intervention. And then this is the confusion matrix. The 89 here means 89 retained customers are correctly identified. 70 retained customers are wrongly flagged as churners. 17 churners are correctly identified, and 24 churners are completely missed. So yeah, what all of this means at this point is that the baseline model that we have performs slightly better, than random guessing, and with an ROC-AUC of 0.52. So while it identifies some churn patterns, it struggles to reliably separate churned customers from retained ones. In particular, the recall for churned customers is low, meaning many churners are still being missed. This tells us that the baseline model is the starting point, but not the final solution. So next, we are going to do some fine tuning. We'll tune the threshold. We'll refine the features and all that. All right, let's do that. Okay, so what is happening here is that by default, logistic regression says if churn probability is greater than 0.5, predict churn, else predict retained. That's 0.5 rule is arbitrary. But for churn problems, it's usually wrong. So here the business goal is to catch more churners, even if that means more false alarms. So we will intentionally lower the churn. We will intentionally lower the threshold. And to do that, the probability that we get from here is mostly gives values like 0.12, 0.37, blah 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 blah. So, and these are risk scores, not decisions. So we will choose a new threshold. And we'll start simple. Instead of the 0.5, that is the arbitrary number, we would lower it to 0.3. Yeah. We apply the threshold after the model has been trained and the probabilities have been generated. So this will allow us to adjust how aggressively the model flags churn risk without retraining or training underlying model. All right, so let's rerun. So after we called the prediction thresh into the confusion matrix and the classification reports, we got this. These were the results that we got. So let's explain. First, if you can notice, the recall for the churn jumps from 0.41 in the first one straight to 0.98. Also, the confusion matrix changed massively. In the new one, 40 churners are correctly caught. One churner is missed. 155 retained customers are falsely flagged as churners, and only 4 retained customers are correctly identified. This is an extreme high recall settings. Now let's explain the classification report. So for the changed customers, we can see that the precision is 0.21, the recall is 0.98, and we have an F1 score of 0.34. What this means is that this model with the fine-tuned threshold now catches almost every single channel. From a retention standpoint, this is very powerful. Yes, many alerts are false positives, but if you ask me, missing channels is actually more expensive than contacting extra customers. So, in my opinion, this is acceptable in early warning systems. And then for the retained customers, we can see a precision of 0.8 and a recall of 0.03. So what this means is that this model almost never convincingly says somebody will stay. It flags nearly everyone at risk. And this is the cost of aggressive thresholding. We also have an accuracy of 0.22 now. We can ignore it, but because it looks awful, yes, but it is quite irrelevant in churn problems with asymmetric costs. So what are we doing here? By lowering the decision threshold, the model prioritizes capturing nearly all churn risk customers. While this significantly increases false positives, yes, it reduces the risk of missing customers who are likely to churn. So we are aligning with proactive retention strategies. So next, we can keep this logistic regression as baseline plus high covariance. Then we propose improvements, or we can improve precision by feature engineering, and then maybe you try decision tree or random forest, or we'll combine the models. So, let's go ahead and improve precision. All right, so we will do feature engineering. We would increase the precision of the features because many of them are weak individually. So we would strengthen them by encoding intents and friction. So we'll look at the spender flag, and the engagement. So we would we would strengthen each feature individually, and we would do this just after importing the data sets and we run the before we run the training pipeline. All right, so let's do that. Yeah, for the service friction. Yeah, and then we add a spender flag, a high spender flag, and then we'll flag those who spend a lot in the app monthly. We'll spend a lot monthly. So and then we'll do one for disengagements, people that have low engagement, low login frequencies, we also flag them as well. All right. So now we would update the feature list because we have added some stuff. Yeah, so just add the new ones that we did. And so yeah, we intentionally removed the noisy raw service categories, and then we kept engineered signals instead. So this hopefully improves precision. Let's run it again. All right, so basically uh in the we added the new features before splitting them, so we just cut it and then we put them after. All right, so yeah, now we got it. So after the feature engineering and with a threshold of 0.3, we had this. And here here was a very high recall training model. So with the threshold of 0.3, we had a high recall pre-screening model and a clear evidence that precision needs improvement. Yeah. So I decided to increase the threshold from 0.3 to 0.4. And here we actually got something that could balance it. Accuracy increased, recall for the retained customers also increased the bits. So now we ended up with 37 channels being cut as compared to the 41. And here we can see that 4 channels are missed. But we only have 124 false positives and 35 correctly identified retained customers instead of 4. So there's a trade-off between missing channels and correctly identifying retained customers. So when we go, you can see that for the chained customers, we have a precision of 0.23 as compared to 0.21. Yeah, and we have a recall of 0.9. So what we are saying here is that we still catch every 9 out of 10 customers, and the precision has improved slightly. So this is a very strong early warning model. And if you move on to the retained customers as well, you can see that precision is now 0.9 and recall is 0.22 as compared to 1 and 0.03. So recall did drop slightly from 1.0 to 0.9. No, precision slightly dropped from 1.0 to 0.9. But recall actually increased from 0.03 to 0.22, meaning the false positive dropped noticeably, and then the model is now actionable. So here it is very, very safe to stop here and say this is good enough to deploy with guardrails. So from a business perspective, at a threshold of 0.4, we catch most channels early and we don't overwhelm retention teams. So now we can tier the interventions instead of blasting discounts. So what do we have? Increasing the threshold reduced the false positives while still capturing the most churned customers. This demonstrates how threshold tuning directly controls the balance between early detection and operational costs. Yeah, so here we have it. Our model does comfortably balances detecting potential churning customers and then the ones that are being retained. All right, so now let's go back to our and then look at what we are done and what we are yet to do. So we've done all of this. What I can say is left to do is to implement techniques like cross-validation. Yeah, we haven't done cross-validation and we are yet to do hyperparameter. All right, so let's go ahead and do that. The stratified five-fold cross-validation we used assessed the model's ability to generalize to unseen data, while it also preserves the original class imbalance. The original class imbalance. So the ROC-AUC scores across the five folds that we get, and including the main ROC-AUC, indicates that the model has limited but consistent discriminative power when distinguishing between churned and retained customers. Also, the relatively low standard deviation of approximately 0.02 suggests that performance is stable across different data splits, meaning the model's behavior is not dependent on a particular trained test split. Well, these results highlight that while the model captures some churn-related patterns, there's significant overlap in customer behavior, and therefore, further feature enrichment or alternative modeling approaches would be required to achieve stronger predictive performance. But for this particular simulation, it is okay to end it here. And if you would like us to continue and build upon this model, whether we seek alternative modeling practices or we go further with feature engineering, indicate in the comments and drop a like. So, to wrap things up, in this project, we didn't just build a churn model. And if you were paying attention, we went through the full decision-making process behind one, from understanding the data to evaluating the trade-offs, to fine-tuning thresholds, and validating performance. This is what real data science looks like in practice. Projects like this are what bridge the gap between learning tools and solving real business problems. If you are trying to move from theory into real-world data work, Understanding this process matters more than memorizing algorithms, in my opinion. So if you found this helpful, don't forget to like, subscribe, and turn off that bell so that when we post more videos, you'll be the first to find out. Once again, this is Ed doing data. Thank you for watching.